Good evening, everyone. Titmus here. Today, we're going to learn about Atwood machines and simple pulleys. Here we go. Consider two objects with different mass. If we drop them simultaneously, they will fall side by side at the same rate, right? So what if we connect them with a string over a pulley? You might expect that they will still fall at the same rate, but the string will stop them from moving, and so they will actually just stay still. But then again, you probably have some nagging intuition that the heavy side will fall down, dragging the light side up. And you'd be correct. Remember, your intuition about what will happen is usually right. Your intuition about why it happens, well, that's another story. All right. So we've got this setup with two different weights connected by a string over a pulley. This is called an Atwood machine, named for George Atwood, who invented the device to slow the constant acceleration of objects, making them easier to study gravity, and to verify Newton's second law. Okay. So let's make this example a little bit more explicit. We will call this mass M1, and let's say that's 4 kilograms. And we'll call this mass M2, and let's say that's 8 kilograms. We have two questions that we want to answer. One, what is the acceleration of each block? And two, what is the tension in each side of the string? Now, there are a few assumptions that we're going to make that will simplify our analysis of this system. 1. The string does not stretch. This is good because it means that if one block moves, the other one will move exactly the same amount. This means that we can actually modify question A a little bit to say, what is the acceleration of the blocks? They will both have to have the same acceleration because they're connected with a string that doesn't stretch. Second assumption is that the string is massless, or at least its mass is so small compared with the weights that we don't have to worry about it. And this is good because we're not concerned with the fact that as the thing moves, the balance of the weight shifts because more string is on one side than the other. We don't want to have to worry about that. The third assumption is that the pulley, the wheel itself, is frictionless and massless. Eliminating friction is always a good idea when we're trying to understand a new physical situation, and assuming that the wheel has no mass means we don't have to worry about the energy needed to spin the wheel. We'll talk about that later when we get to moment of inertia. While we're at it, let's just toss in that we're going to assume that air resistance is negligible. Okay? Right. So with those assumptions set, we can start to approach the problem. And there are really two different ways to approach this problem: the easy way and the hard way. The easy way involves treating the two masses connected by the string as a single thing. We're going to call it a system. Now, you've actually been using a system approach in many situations. For instance, any of the speed and distance problems that involved driving a car, we treated the car and the pistons in the engine and the wheels and the people inside all together as a system. The motion of the individual components did not affect the overall motion of the system, of the car. This is because they applied internal forces, and internal forces never affect the overall motion of the system. Internal forces can cause something called perturbations, which are small bumps. For instance, the passengers in a car can kind of jump up and down, and the car will bounce, but it will always return to what it was doing before the people were jumping up and down. Okay, so the only things that affect a system are external forces. The system approach is going to be really useful for finding the acceleration. But because the string is internal to the system, The system approach won't be able to tell us about the internal forces, which include the tension. Bummer. That's okay, we'll cross that bridge when we get to it. Okay, so the first thing to do is to establish a positive direction of motion. This is a bit weird, because we know if one weight moves up, the other moves down, and vice versa. So the easiest thing we can do is define the positive direction as the way the whole thing is going to move, which wraps around the top of the pulley just like the string does. I'm not ready to draw a free body diagram because we've got this extended object. It's hard to just put it all together as a single point. But I'm going to draw the forces on the diagram. Notice that FG2 is positive because on the right side, our positive direction points downward. But FG1 is negative because on the left side, the positive direction points upward. Now this next step is optional, but I think a lot of people find it helpful. So we're going to reimagine the situation stretched out horizontally. So we have two masses connected by a string stretched sideways. We'll call the positive direction to the right. We're just unbending our axis here in the same way that we unbend the mass and string system. So now we have FG2 pointing to the right, positive direction, and FG1 pointing to the left, negative direction. Then we redraw it again. This time we're going to eliminate the string, since the string forces are all internal. So now we have the combined mass, M1 plus M2, and FG2 points to the right, FG1 points to the left. And now this is something that we can use to draw a free body diagram. With the free body diagram, this thing is now easy to solve. First, we list our knowns. We should include masses, forces, accelerations. It might be useful to write down what g is, especially if it's on a different planet, which an Atwood machine problem very well could be on a different planet. And then we can use Newton's second law to relate the forces to the acceleration. We get that acceleration is equal to the net force divided by the mass. But we know that the net force is composed of Fg2 in the positive direction and Fg1 in the negative direction. And we know that the mass of the system is the combined mass of m1 plus m2. So we get that the acceleration is equal to Fg2 minus Fg1 all over m1 plus m2. Then it's worth recognizing that calculating the forces of gravity is simple. Fg1 equals m1 times g, and Fg2 equals m2 times g. Substituting those in, we get acceleration equals m2 times g minus m1 times g, all over m1 plus m2. And finally, we can factor out the common g to get acceleration equals m2 minus m1 times g, all over m1 plus m2. And now we can plug in our knowns. And this gives us an acceleration of 3.27 meters per second squared. All right, we got the acceleration. And that is what we can do using the system approach. It's worth noting that once we've got the acceleration, a whole range of kinematics type problems opens up. So we could think about how much time will it take the machine to move some distance. We could even flip the whole thing around and start by measuring the time to move some distance and use that to figure out what g is, or maybe to figure out what one of the masses is, right? So there's lots of different ways this situation can be rearranged, and be prepared for that. Now, the next thing we want to do is answer question B. We want to figure out the tensions in each side of the string. Now, because the string is internal to the system approach doesn't work. We have to split the system up. So we're going to focus on M1 and M2 separately. Let's take a look at M1 first. The old axis that we had curved around the pulley, that doesn't apply anymore because we're looking at these things individually. That was for the system. Now we're just looking at M1, so we redefine our axis. Let's make up the positive direction. First, we draw a free body diagram. FG1 pulls down, the tension FT1 pulls up. We know it is accelerating upwards, so the tension must be larger than FG1. We can list out our knowns, mass, G, FT1, and actually, this is huge. We know what the acceleration is because we found it in part A. And then we can use Newton's second law to relate the forces to the acceleration. We get that net force equals mass times acceleration. And we know that net force is composed of Ft1 in the positive direction and Fg1 in the negative direction. So Ft1 minus Fg1 equals mass times acceleration. What mass are we talking about here? Well, now it's just m1, not the combination. And we might as well substitute in m1g for the force of gravity while we're at it. And this gives us Ft1 minus m1g equals m1 times acceleration. Solving for Ft1, we get Ft1 equals m1a plus m1g. Or factoring out m1, we get Ft1 equals m1 times a plus g. Plugging in our numbers gives us 52.32 newtons. Great. All that's left to do now is the exact same thing for Ft2. And we're going to go through the same steps. We redefine the axis. Up is positive. Draw the free body diagram. Ft2 now must be smaller than Fg2 because m2 is accelerating downwards. We list out our knowns, mass, g, acceleration. Here we make the acceleration negative because now it's accelerating downwards, which is the negative direction. Then we have Ft2, our unknown. It's worth pointing out that the acceleration is not equal to g. And that might seem obvious, but a lot of times people think that the acceleration always equals g. But that's only true if the object is in free fall, which this isn't because the string is also applying a force to the block. Anyway, now again we can use Newton's second law to relate the forces to the acceleration. We get that net force equals mass times acceleration. And we know that net force is composed of Ft2 in the positive direction and Fg2 in the negative direction. So we get Ft2 minus Fg2 equals mass times acceleration. What mass are we talking about here? Well, now it's m2 instead of m1. And again, we might as well substitute in m2g for the force of gravity while we're at it. This gives us Ft2 minus m2g equals m2 times acceleration. Solving for Ft2, we get Ft2 equals m2a plus m2g, or factoring out the m2, Ft2 equals m2 times a plus g. Plugging in our numbers, and don't forget that a is negative, we get 52.32 newtons. Oh my gosh. Now, this is really quite important. What we have just found is that Ft1 is exactly the same as Ft2. And this tells us something really important about how pulleys work. Pulleys will modify the direction that a rope pulls, but they do not change the amount of tension in the rope. The tension in the rope on one side of the pulley wheel will always be exactly the same as the tension on the other side of the pulley wheel. And we're going to take a closer look at that in the next lesson on pulleys. But that's it for today. So all we have to do when we're analyzing an Atwood machine, the simplest thing is to start with the system approach. Because the system approach is easy. It gets rid of all of that mess in the middle, the middleman, the string, right? So we start with the system approach, and that tells us the macroscopic motion of the system. It tells us how it's going to accelerate, how it's going to move. We start with the system approach, figure out the acceleration. Once we have the acceleration, it's much easier now to focus on the individual components, M1 and M2, and do a typical free body diagram approach. Nothing funky, no weird curving axes or anything like that. Nice and straightforward. Okay, start with the system approach, end with the individual approach. Bob's your uncle. Okay, so that's it. I hope you guys have a great day. Let me know if you have any questions, and I'll see you soon.